Hello and welcome to Selection Sathi. Today we will master time and space complexity, a must-know topic for GATE CSE, placements, and coding interviews. Let's understand how to analyze algorithm efficiency using Big O notation. Big O notation describes the upper bound of an algorithm's growth rate. We write T of n equals O of f of n, meaning for large n, the running time is at most a constant times f of n. The key rule is drop constants and keep only the dominant term. For example, O of 5n squared plus 3n simplifies to O of n squared. Let's look at the common complexity classes in increasing order. O of 1 is constant time, like array axis. O of log n is logarithmic, like binary search. O of n is linear, like scanning an array. O of n log n is seen in efficient sorting algorithms like merge sort. O of n squared is for nested loops, and O of 2 to the n is exponential, like brute force subset generation. Space complexity measures the memory an algorithm uses. It includes both input space and auxiliary space. Auxiliary space is the extra space beyond the input. In-place algorithms like insertion sort use O of 1 auxiliary space. Recursive algorithms use stack space proportional to the recursion depth. For example, recursive Fibonacci uses O of n stack space. Here are the key rules for analyzing loops. A single loop from 1 to n is O of n, two nested loops each running n times give O of n squared. A loop where the variable halves each time, like while n greater than 0, n equals n divided by 2, that's O of log n for consecutive loops, add their complexities, and keep the dominant term. Let's analyze a nested loop. For I from 0 to n, for j from 0 to n, print I plus j. The outer loop runs n times. For each iteration, the inner loop also runs n times. Total operations are n times n, which is n squared. So the time complexity is O of n squared. Now let's prove that binary search is O of log n. At each step, we have the search space. Starting from n, after k steps we have n divided by 2 to the k elements. The search ends when n divided by 2 to the k equals 1. Solving 2 to the k equals n, so k equals log base 2 of n. Therefore, binary search runs in O of log n time. What about the space complexity of recursive Fibonacci? The time complexity is O of 2 to the n because of overlapping calls. But for space, only one branch of the recursion tree is active at any time. The deepest the call stack goes is from fib of n down to fib of 1, which is n frames. So the space complexity is O of n, not O of 2 to the n. Let's compare sorting algorithms. Bubble sort is O of n squared in both average and worst case. Merge sort is always O of n log n, but uses O of n extra space. Quick sort is O of n log n on average, but O of n squared in the worst case. Counting sort runs in O of n plus k, where k is the range of input values. For comparison-based sorts, O of n log n is the theoretical lower bound. Here are the key takeaways. Always simplify by dropping constants and lower-order terms. If a loop variable halves or doubles each step, think of log n recursive space complexity equals the maximum call stack depth, not total calls. And remember, O of n log n is the best possible for comparison-based sorting. For more concept videos like this, download the Selection Sathi app. Like and subscribe. Thank you.